So we're going to continue Chapter 5, Sequences, Mathematical Induction and Recursion. Continue with an application, the correctness of algorithms. What does it mean for a computer program to be correct? Each program is designed to do a specific task, like calculating the mean or median of a set of numbers, compute the size of the paychecks for a company payroll, or rearrange names in alphabetical order. We will say that a program is correct if it produces the output specified in its accompanying documentation for each set of input data of the type specified in the documentation. Assertions. Consider an algorithm that is designed to produce a certain final state from a certain initial state. Both the initial and final states can be expressed as predicates involving the input and output variables. Often, the predicate describing the initial state is called the precondition for the algorithm, and the final state is called the postcondition for the algorithm. Here are pre- and post conditions for some typical algorithms. Algorithm to compute a product of non-negative integers. Precondition, input variables m and n are non-negative integers. Postcondition, the output is the output variable p equals m times n. Or an algorithm to find quotient and remainder of the division of one positive integer by another. The precondition would be the input variables a and b are positive integers. Postcondition would be the output variables q and r are integers such that a equals bq plus r, and r is less than b but greater than or equal to 0. The algorithm to sort a one-dimensional array of real numbers. Precondition, the input variables a1, a sub 2, a sub 3, etc. to a sub n is a one-dimensional array of real numbers. And the postcondition would be the output variable b1, b2, etc. to bn is a one-dimensional array of real numbers with the same elements as a, but with the property that bi is less than or equal to bj whenever I is less than or equal to j. Loop invariance. The method of loop invariance is used to prove correctness of a loop with respect to certain pre- and post conditions. It is based on the principle of mathematical induction. Suppose that an algorithm contains a while loop and that the entry to this loop is restricted by a condition G called the guard. Suppose also that assertions describing the current states of the algorithm's variables have been placed immediately preceding and immediately following the loop. The little typo there, they didn't put the immediately following the loop. The assertion just preceding the loop is called the precondition for the loop, and the one just following it is called the postcondition for the loop. The annotated loop has the following appearance. Precondition for the loop, while G, statements in the body of the loop, none contain branching statements that lead outside the loop, and finally the postcondition for the loop. A loop is defined as correct with respect to its pre- and post conditions if and only if, whenever the algorithm variables satisfy the precondition for the loop and the loop terminates after a finite number of steps, the algorithm variables satisfy the post condition for the loop. A loop invariant is a predicate with the domain of a set of integers, which satisfies the condition for each iteration of the loop. If the predicate is true for the iteration, then it is true after the iteration. Furthermore, if the predicate satisfies the following two additional conditions, the loop will be correct with respect to its pre- and post conditions. The predicate is true before the first iteration of the loop. If the loop terminates after a finite number of iterations, the truth of the loop invariant ensures the truth of the post condition of the loop. The following theorem, called the loop invariant theorem, formalizes these ideas. It was first developed in 1969. It says, let a while loop with guard G be given, together with pre- and post conditions that are predicates in the algorithm variables. Also let a predicate I sub n, I of n, called the loop invariant be given. If the following four properties are true, then the loop is correct with respect to its pre- and post conditions. Number one, the basis property. The precondition for the loop implies that I of 0 is true before the first iteration of the loop. The inductive property, number two. For every integer k greater than or equal to 0, if the guard G and the loop invariant I of k are both true before an iteration of the loop, then I of k plus 1 is true after an iteration of the loop. Number three, eventual falsity of the guard. After a finite number of iterations of the loop, the guard G becomes false. Correctness of the post condition. If big N is the least number of iterations after which G is false and I of n is true, then the values of the algorithm variables will be as specified in the post condition of the loop. The loop is designed to compute the product m times x for a non-negative integer m and a real number x without using a built-in multiplication operation. For this example, prior to the loops, variables I and product have been introduced and given initial values I equals 0 and product equals 0. Precondition. M is a non-negative integer, x is a real number, I equals 0 and product equals 0. While I does not equal m, do the following. Product equals product plus x, and I equals I plus 1. Post condition, product equals m times x. Let the loop invariant be I of n equals I equals n, and product equals n times x. The guard condition G of the while loop is I does not equal m. Use the loop invariant theorem to prove that the while loop is correct with respect to the given pre- and post conditions. Basis property. I of 0 is I equals 0 and the product equals 0 times x, which is true before the first iteration of the loop, because 0 times x is 0. The inductive property. Suppose k is a non-negative integer such that g and I of k is true before an iteration of the loop. Then as execution reaches the top of the loop, I does not equal n, product equals k times x, I equals k. Since I does not equal m, the guard is passed and statement 1 is executed. Before execution of statement 1, product the old product equals k times x. Thus, the execution of statement 1 has this following effect. New product equals the old product plus x, or k of x plus x, which equals k plus 1 times x. So, after execution statement 2, I new is equal to I old plus 1, which is equal to k plus x. Hence, after the loop iteration, statement I of k plus 1, namely I equals k plus 1 and product equals k plus 1 times x, is true. This is what we needed to show. Eventual falsity of the guard. The guard G is the condition I does not equal m, and m is a non-negative integer. By 1 and 2, it is known that for every integer n greater than 0 or equal to 0, if the loop is iterated n times, then I will equal n, and product will equal n times x. So after m iterations of the loop, I will equal to m. Thus, G becomes false after m iterations of the loop. Correctness of the post condition. According to the post condition, the value of the product after execution of the loop should be m times x. But if G becomes false after big N iterations, I equals m. And if I of n, big N, is true, then I equals big N and product equals big N times x. Since both conditions, G is false and I of n, big N, are true, both conditions are satisfied, m equals I, which is equal to n, big N, and product equals m times x as required. Seems like a lot of details to go through to just multiply two numbers, but it's demonstrating a point. Correctness of the division algorithm. The division algorithm is supposed to take a non-negative integer a and a positive integer d and compute non-negative integers q and r such that a equals dq plus r, and r is between 0 and d. Initially, the variables r and q are introduced and given the values r equals a and q equals 0. The crucial loop, annotated with pre and post conditions, is the following. Just this algorithm here, where the primary lines of code are the r equals r minus d, the divisor, and quotient is increased by 1, as long as r is greater than or equal to d. Correctness of the Euclidean theorem. The Euclidean algorithm is supposed to take integers a and b with a greater than b and b greater than or equal to 0 and compute their greatest common divisor. Just before the crucial loop, variables a, b, and r little a, b, and r have been introduced with little a equals big A, little b equals big B, and r equals b. And then the crucial loop is r equals little a mod little b, a equals will equal to b, and then b will equal to r in the loop as long while b is not equal to 0. So writing algorithms in loops. But let's see here. That was 5, 5, so we're 5, 6 now. Continuing with section 5.6. Defining sequences recursively. Well, a sequence can be defined in a variety of different ways. One informal way is to write the first few terms with the expectation that the pattern will be obvious. We might say, for instance, the sequence 3, 5, 7, etc. Unfortunately, misunderstandings can occur when this approach is used. The next term of the sequence could be 9 if we mean a sequence of odd integers, or it could be 11 if we mean a sequence of odd prime numbers. So the second way of defining a sequence is to give an explicit formula for its nth term. So the sequence can be specified by writing this, for example. The advantage of defining a sequence by this method is that each term of the sequence is uniquely determined and can be computed in a fixed finite number of steps by substitution. The third way to define a sequence is to use recursion. This requires giving both an equation called a recurrence relation that defines each later term in the sequence by a reference to earlier terms, and also one or more initial values for the sequence. Sometimes it is very difficult or impossible to find an explicit formula for a sequence, but it is possible to define the sequence using recursion. Definition. A recurrence relation for a sequence, A, for example, is a formula that relates each term A sub k to certain of its predecessors, like A sub k minus 1 or A sub k minus 2, etc. If I is a fixed integer, the initial conditions for such recurrence relations specify the values of A sub 0, A sub 1, A sub 2, all the way up to A sub I minus 1. I depends on k. The initial conditions specify the values of A sub 0 to A sub m, where m is an integer with m greater than or equal to 0. So example, define a sequence C sub 0, C sub 1, etc. recursively as follows. For every integer k greater than or equal to 2, C sub k equals C sub k minus 1 plus k times C sub k minus 2 plus 1. C sub 0 equals 1, and C sub 1 is equal to 2. So you would need to go through, to find C sub 4, you would need to calculate C sub 3 and C sub 2 beforehand. So it's not a fixed number of iterations of substitution. C sub 2 would be C1 times C, 2 times C0 plus 1. Substitute K equals 2, and you get 5 when you calculate it all out. C sub 3 is C sub 2 plus 3 times C sub 1 plus 1, which gives you 12, right? Yeah. And then C sub 4 is C sub 3 plus C sub 4 times C sub 2 plus 1, which is equal to 33. There's more than one way to write a recurrence relation, usually. Since let S sub 0, S sub 1, S sub 2, etc. be a sequence that follows this recurrence relation. For every integer k greater than or equal to 1, S sub k equals 3 times S sub k minus 1 minus 1. Explain why the following statement is true. For every integer k greater than or equal to 0, S sub k plus 1 equals 3s sub k minus 1. Well, in informal language, the recurrence relation says that any term of the sequent equals 3 times the previous term, minus 1. Now, for any integer k greater than or equal to 0, the term previous to s sub k plus 1 is s sub k. Thus, for any integer k greater than or equal to 0, s sub k plus 1 equals 3s sub k minus 1. Sequences that satisfy the same recurrence relation. Let A and B be sequences that satisfy the recurrence relationship relation that the kth term equals 3 times the k minus 1 term for every integer k greater than or equal to 2. Now suppose the initial conditions for the sequences are different. That A sub 1 equal 2 and B sub 1 equal 1. Well, the sequences follow different paths because of the different initial conditions. 6, 18, 54 versus 3, 9, and 27. So the sequences are different even though they have the same recurrence relation. The sequence of Catalan numbers, named after Belgian mathematician Eugene Catalan, arises in a remarkable variety of different contexts in discrete mathematics. It can be defined as follows for each integer n greater than or equal to 1. C sub n equals 1 over n plus 1 times n 2n choose n. So show that this sequence satisfies the recurrence relation C sub k equals 4k minus 2 over k plus 1 times C sub k minus 1 for every integer over greater than or equal to 2. So the first in the sequence are going to be 1, 2, and 5. To obtain the kth and the k plus or minus 1 term of the sequence, just substitute k and k minus 1 in place of n in the explicit formula for c sub 1, c sub 2, c sub 3, etc. So, substituting, you get c sub k here and c sub k minus 1 here. And then start with the right side of the recurrence relation and transform it to the left side for each integer k greater than or equal to 2. So you have the substitution, then the formula for n, choose r here, and then rearranging the factors and simplifying. It gets pretty messy in here, but rearrange the factors again and rearrange the consolidate and substituting again the formula for n, choose r, and then definition of that's the definition of c sub k. A bit of a mess, but it's possible. Examples of recursively defined sequences. The Towers of Hanoi. It's most calculating the Towers of Hanoi, moves necessary to do the Towers of Hanoi is typically I want to say, first or second semester programming project. Anybody do that in CS1 or 2? Towers of Hanoi? No? Okay. It might be in algorithms that it's done, I'm not sure. But one of the earliest examples of a recursively defined sequence occurs in the writings of Leonardo da Pisa, commonly known as Fibonacci, who was the greatest European mathematician of the Middle Ages and promoted the use of Hindu-Arabic numerals for calculation. In 1202, Fibonacci proposed the following problem. A single pair of rabbits, male and female, is born at the beginning of a year. Assume the following conditions. Rabbit pairs are not fertile during their first month of life, but thereafter give birth to one new male-female pair at the end of every month, and no rabbits die. How many rabbits will there be at the end of the year? One way to solve this is to plunge right into the middle of it using recursion. Suppose you know that how many rabbit pairs there were at the end of the previous months. How many will there be at the end of the current month? The crucial observation is that the number of rabbit pairs born at the end of month K is the same as the number of pairs alive at the end of month K minus 2. Why? Because it is exactly the rabbit pairs that were alive at the end of K minus 2 month that were fertile during month K. Rabbits born at the end of month K minus 1 were not. Now the number of rabbit pairs alive at the end of month K equals the ones alive at the end of month K minus 1 plus the new pairs newly born at the end of the month. Thus, the number of rabbit pairs alive at the end of the month K is equal to the number of rabbit pairs alive at the end of month K minus 1 plus the number of rabbit pairs born at the end of month K, which equals the number of rabbit pairs alive at the end of month K minus 1 plus the number of rabbit pairs alive at the end of month K minus 2. For each integer n greater than or equal to 1, let f sub n be the number of rabbit pairs alive at the end of month n. And the initial number of rabbit pairs would be equal to 1 in month 0. Yeah, and f sub 1 is 1 as well. Then by substitution into the equation, for every integer k greater than or equal to 2, f sub k equals f sub k minus 1 plus f sub k minus 2. F sub 0 is 1, as already noted, and f sub 1 is equal to 1 also because the first pair of rabbits is not fertile until the second month. Hence, the complete specification for the Fibonacci sequence is as follows. So, f sub k equals f sub k minus 1 plus f sub k minus 2. F sub 0 equals 1, and f sub 1 is equal to 1. To answer Fibonacci's question, compute f sub 2, f sub 3, and so on to f sub 12 to get 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, and finally 233. So at the end of the 12th month, there are 233 rabbit pairs, or 466 rabbits in all. Compound interest. When annual interest rate of I is compounded m times per year, the interest rate paid per period is I divided by m. For instance, if 3% annual interest is compounded quarterly, then the interest rate paid per quarter is 0.03 divided by 4. For each integer k greater than or equal to 1, let P of k be the amount on the deposit at the end of the kth period, assuming no additional deposits or withdrawals. Then the interest earned during the kth period equals the amount on the deposit at the end of the k minus 1 period times the interest rate for the period. The amount on the deposit at the end of the kth period, P sub k, equals the amount at the end of the minus 1 period plus the interest earned during the kth period. So the recurrence relation is defined as follows, defined here. Suppose $10,000 is left on deposit at 3% compounded quarterly. How much would the account be worth at the end of 1 year, assuming no additional deposits or withdrawals? What is the annual percentage yield, which is the percentage increase in the value of the account over 1 year period? So the APY, there's the API, annual percentage rate, APR, and then the annual percentage yield, which is slightly higher. For each integer n greater than or equal to 1, let P of n sub n be the amount on the deposit after n consecutive quarters, assuming no additional deposits or withdrawals, and let P sub 0 be the initial $10,000. Then by equation 5.6.4, with I equals 0.03 and M equals 4, a recurrence relation for the sequence is P of k sub k equals P sub k minus 1 times 1 plus 0.0075, or 1.0075 times P sub k minus 1. The amount on the deposit at the end of the year, 4 quarters, can be found by successive substitution. And it builds up 10,075, then 10,150, 10,226, finally 10,303.39. The annual percentage yield would be then 3.034%. Recursive definitions of sum and product. Addition and multiplication are called binary operations because only two numbers can be added or multiplied at a given time. Careful definitions of sums and products of more than two numbers use recursion. Given the numbers a sub 1, a sub 2, etc. to a sub n, where n is a positive integer, the summation from I equals 1 to n of the a sub I, denoted with that equation, is defined as follows. The summation of I from I equals 1 to 1 equals AI equals AI, or A1. I equals 1 to n, the summation of a sub I equals summation of a sub I, summation from I equals 1 to n minus 1, a sub I plus a sub n, if n is greater than 1. The product is similarly defined with the multiplication of the last term. Prove that for any positive integer n, if the sequences a sub 1, sub 2, sub 3, etc. to sub n, and b sub 1, sub 2, sub 3 to sub n are real numbers, then this equation holds true. Well, the proof is by mathematical induction. Let the property P of n be the equation given here. We must show that P of n is true for every integer n greater than or equal to 1. We do this by mathematical induction on n. To establish P sub 1, or P of 1, we must show that show that this is true. To show that P of 1 is true. Go back? Yeah. Summation of I from I to 1 equals 1 to 1 of a sub I plus b sub I equals the summation of a sub I and b sub I. Got it? All right. And now, by the definition of summation, This simplifies to that, and that is also by the definition of summation. This is finally true. So P of 1 is true. Now you need to show that for every integer k greater than or equal to 1, if P of k is true, then P of k plus 1 is also true. Suppose that k is any integer with k greater than or equal to 1, and that the sequence of a from 1 to k plus 1 and b from 1 to k plus 1 are real numbers such that this equation is true, the inductive hypothesis. You must show that the summation with k plus of I to k plus 1 is also true. Well, now the left-hand side of the equation is k is this equation is expanded out to this by the definition of summation, and then by the inductive hypothesis we put that we can substitute that, and then rearrange the terms, and then consolidate it by using the definition of summation, which equals the right-hand side of the equation, which is what was to be shown. And that will be about it for that slide deck. Do we have enough time for another one? Or do you want to call it an early day? A lot to wrap your head around today? Yeah, we'll call it a day after this. We'll get into the next section on Thursday. In the meantime, have a wonderful day.